Hello everyone, my name is Rui Wu, a Ph.D. student from UMass Law, Electrical and Computer Engineering Department. I'm very glad to have this opportunity to present our work on Project 1.5, Distributed Sensing Textile for Bridge Monitoring. Let me briefly introduce our fiber optic lab. Our focus research area are optical fiber sensors, biosensing, and biomedical devices, and also optical image. We have finished different projects with national departments and big companies. And Professor Tzuyang Yu's lab from Department of Civil Engineering, they are experts on remote sensing and concrete structure analyzing. Today, I will cover two main distributed fiber sensing systems applied on our school's pedestrian bridge and also SALMON 4 River Bridge. Here is the outline of the presentation. First, I will introduce the project background and why this project is important. Then, I will explain the technique we use for distributed sensors and how we fabricate it. Next, I will go through two field tests of our sensing textile and make summaries of our lessons learned in the conclusion part. Structural health monitoring is a process of collecting, interpreting, and analyzing data from structures in order to determine its health status and remaining lifespan. The accumulated degradation and other factors will reduce the structure's disaster resilience ability and can sometimes lead to partial failure or complete collapse of the structure. The potential for such accident is a direct threat to the safety of both life and properties. With these raising concerns, health monitoring has become one of the top research focus areas in recent years. Despite of the tremendous research has done in past few decades, still there are major issues and challenges. For example, how to monitor large-scale structure and sensor reliability. And also one important problem is to develop a distributed sensing system. By using fiber optic sensors, we can take the advantages of fiber reliability and the ability of distributed sensing to solve those issues mentioned above. The technique we use in distributed fiber sensing system is called Brilliant Optical Time Domain Refractometer. Brilliant frequency takes place when a photon from an incident light wave is transformed into an scattering photon. The optical frequency of a backscattering light by the Brilliant scattering is up or downshift from the incident light by the Doppler effect. Shown in Figure 1, when fiber applies strain or temperature change, the Brilliant frequency will shift, and by monitoring the frequency shift, the whole fiber can be a sensor. Here, I will introduce how we fabricate the sensing textile. As shown in Figure 1, the red line of U shape indicates the single-mode fiber to collect strain data. The orange line was multimode fiber connected to distributed temperature sensing machine as temperature reference. And 8 strain gauges was fixed along the textile to verify strain data. All the fibers were embedded on the textile using an embroidery method. Video shows how the embroidery machine works. By importing the design into the machine, we could have flexible layout of distributed sensing area on our target. Next, I will talk about the application of our sensing textile. The field test on pedestrian bridge on our campus. The bridge is a one-span steel rust bridge with a span of 92 feet, and sensing textile prototype was planned to be installed on one side of the bridge. The prototype of sensing textile has two single-mode fibers. One connected to BOTDR for data collection, and the other was a backup. The length of each fiber was 28 meters and was laid down at one side of the pedestrian bridge. We used 3M high-strength adhesive to fix the textile on the floor and remove air bubbles before curing. Here's how we did the test. The pedestrian bridge was loaded with 707 kilograms weight at 7 meters location. You can see the loading test photo in Figure 1. We used concrete bars and 6 people as weight. And we tried different parameters of BOTDR to achieve better signal performance. Here's the experiment result. Figure 1 shows the data before and after curing process. And it is obvious that the curing provides a pre-strand to the textile. We took 5 times continuous collected data of unloaded bridge as baseline and do the same thing with the loaded bridge. We averaged those 5 trials of data and compared data with the baseline. At 117 meters location, we found the Boolean frequency shift corresponds to 10 microstrand. We added the loading at 7 meters location from the starting point of the bridge, and our launching fiber was 110 meters. So the frequency change represents the strength of the sensor collected on the loading. Since we cannot find more larger weight applied on the bridge, the frequency response of this fiber sensing prototype was very small. We're now trying to use other fiber technique to improve sensing sensitivity and get more data on this pedestrian bridge. After we have the experience of pedestrian bridge, we started to do further research on bridge monitoring. The Salmon Fall River Bridge located in New Hampshire, and we have train passing by the bridge. We install the sensing textile at the bottom side of the bridge, which you can see the red box indicate the sensors located in the Figure 2. Here, I will talk about the sensor design and installation. One fiber with U-shape was distributed across the width of textile, and the length was 11 meters. Experts from ARE helped us to install the sensor with epoxy, and we connected the system under the bridge. The epoxy took 1 day for curing, so we collected data before and after curing process. It is surely that it provides pre-strand to the system. As shown in Figure 1, the section ACB is the sensing section, and point C was the U-turn part in the design. In Figure 2, we can see the DA part was the connecting fibers hang down from the bridge. The BE part was used as temperature compensation part, since they are not fixed in the epoxy and free from pre-strand. The sensing section was ACB and the length was 22.46 meters. We also tested the data when a train was passing by the bridge. From Figure 1, we can see the lines with stars was the data under train. We could obviously observe the frequency change between those data. The strand difference among tests without strand were at low level of 2.01 and minus 26 microstrand. The trend variation between tests under trend and without trend were up to 87.8 microstrand. This demonstrated that the system can indicate when a train passing by a bridge. After installation of the sensing system, we continuously come back to the bridge and recorded the data from BOTDR over 18 months. As shown in Figure 1, the BOTDR data after long term has a good agreement, and the biggest difference appears on junction 1 and junction 2. We can see these junctions on Figure 2. The gap between different pieces of steel caused the dried out of epoxy. and also the junction section are more sensitive to strain. So the unstable noise was introduced to the system at these two locations. After these two field tests of sensing textile, we have accumulated experience of design and fabricate fiber sensors using embroidery method. The BOTDR technique was demonstrated to be a practical method for distributed sensing system on structural health monitoring. The fiber sensing system has good repeatability and reliability over 18 months. In the future, we try to improve a proper way to protect the fiber connection under the bridge, and also we try to develop some new signal process method to reduce noise. Thank you so much for listening.